In this lesson, we're going to learn how to graph exponential functions using transformations. Let's begin with this example where there are 50 bacteria microbes in a petri dish. They are doubling every hour. Complete the table below to model the number of microbes. So we're starting with 50. So I'm going to say that's before any time passes. In 1 hour, they're going to double to 100. The end of the next hour, double again to be 200. The end of the third hour, double again to 400. If I went to the fourth hour, it would be 800, and it would continue in this format. This table can be modeled by an exponential function. When something doubles or triples every span of time, it's going to be an exponential function. So since it's doubling, that's going to be the base of my power. And the exponent will actually be the variable x, where x represents hours, and y will be my number of microbes. So if you think about this, well, 2 to the first is 2, 2 to the second is 4. That's certainly not the scenario I have here. But what do I have is that it starts with 50. So if I do 50 times, well, let's see, 2 to the first would be 100, which would be this value. If I did plug in a 0, this would be 2 to the 0 would be 1, and 50 times 1 is 50. So this right here is an exponential function modeling this scenario. So the general form of an exponential function, it looks like this, where b, your base, is also known as your growth or decay factor, depending if it's your population's growing or if it's decaying. And this a value is like your initial value or your starting point, where we had 50 bacteria in the previous example. Let's look at a graph of a basic exponential function. So you can see what it looks like on the screen, and I'm going to adjust the b value, the base, and watch what happens. So as I make b greater, it's all the way up at 3, notice that it is growing at a quicker rate. Keeps getting steeper and steeper. Whereas if I go the other direction, it starts decreasing, or I should say, not growing as steeply. Look at it now. When I get to 1, check it out, it's exactly a horizontal line, and now it's less than 1, it's actually decaying. Your population would be decreasing if we're looking at a population, and steeper that it's declining. So for what values of b is that true for? Well, it's decaying, it looks like, when it is greater than 0, because there it is at 0, and now it is exactly a horizontal line. But when it is greater than 0, but less than 1, it was decaying, okay, known as exponential decay. But when it was greater than 1, we saw it increased, and that's known as exponential growth. Okay, so let's summarize these two scenarios. So talking exponential growth first, we just said that's when the base of your function is greater than 1. It wouldn't equal 1 because 1 to any power is just going to be 1, and y equals 1 would be a horizontal line fixed at 1. All right, so I'm going to graph my basic function. We saw on the last graph that it crossed right here at 0, 1. And if it was exponential growth, it sharply increased. And hopefully you noticed that it approached 0, but it would never ever equal 0. To help you understand that for just a second, if we look at y equals 2 to the x, that would be exponential growth, and we just pick some values like 1, 2 to the 0 is 1, 2 to the first is 2, 2 to the second is 4, 2 to the third is, make that a 3, excuse me, 2 to the third would be 8. Now if I made it smaller, like -1, 2 to the negative first is 1/2. 2 to the negative second would be 1/4. Okay, so it's getting smaller and smaller as I get more negative, but it will never become 0. There's no way it can be 0. So we have an interesting word right here. There is what's known as a horizontal asymptote at y equals 0, which is a horizontal line that your graph or your curve will approach, but it's never going to cross over it. So let's check out the domain. So this would be negative to positive infinity. The range, however, it's going to start at 0, but we just said it never touches it, so it goes 0 to infinity. And the end behavior, as x approaches positive infinity, that'd be on the right side, the graph is going up towards positive infinity, but as x goes towards negative infinity on the left, it's approaching 0. Right, so then let's look at exponential decay. This is a scenario where your b value is between 0 and 1, not equaling either. So how this switches is there's still this point at 0, 1, okay, but it's decreasing from left to right. It's drastically decreasing. So this also has this horizontal asymptote at y equals 0. It has the same domain, and it actually has the same range. The end behavior is just a little different. As x approaches positive infinity, the graph is approaching 0. But on the left side, as the graph approaches negative infinity, as we move to the left, the graph goes up towards positive infinity. So those are the general exponential growth and decay functions. We're going to use transformations to graph other exponential functions. So what we're going to do is we're going to begin with a function looking at it in the form of this a coefficient out front, your initial value. You can see something happens to your x value, and you know that is a horizontal shift. And hopefully you remember that horizontal things always work opposite of what our brain thinks. So if you have a minus, it's actually going to go to the right. If you have a plus, it'll go to the left. Okay, we'll move this up or down. I encourage you to look at either Schoology, where I have some apps where you can do some manipulations and look at this, or there is a GeoGebra one that is great as well. Okay, so for this example, here's my a value, here's my growth factor of 2, which is b, and I can see that this is going to have a shift 4 to the right and 1 down. Those are translations. So what I'm going to end up doing with this is I'm going to think about the parent function. So we're going to graph this function first by looking at the parent function, okay? And the parent function here is I'm going to just take the first part of this function, the 3 times 2 to the x power, and that's going to be the parent function that I look at, okay? And I'm going to think about the points I need to graph this. And the points I'm always going to use are 0, a, okay? So why is that? I'll kind of explain why, and then we're just going to always use that. So if I plug in 0 into this function, into the parent function, I would have 2 to the 0, which is going to be 1, and then it's 3 times that. So 3 times 1 would be 3. So if I plug in 0, I'm always going to end up with the a value, which is 3. Then I go 1 unit to the right. Well, if I go 1 unit to the right, and I plug that into my function here, 3 times 2 to the first power, what do I really get? I'm going to get a times b, which is 6. I am always going to have that nice little pattern. So if I always stick with these first 2 ordered pairs, 0a and 1ab, as my starting point, then all I have to do is do my translations, left and right or up or down. So we said this is going 4 units to the right. So I'm going to take my x values and I'm going to add 4 onto each of them. So 0 plus 4 is 4 and 1 plus 4 is 5. Now I'm going to look at my y values. We said we need to shift this down 1. So each of these y values will get 1 subtracted from it to get 2 and 5. Then I go over to my coordinate plane and I plot my ordered pairs 4, 2, and 5, 5. And I know that this is exponential growth because my b value was larger than 1. My horizontal asymptote would have been shifted. Typically it begins at y equals 0. But because it was shifted down 1, I draw my horizontal line right here at y equals -1. And then I draw my exponential growth curve that will hug that asymptote until it shoots up pretty quickly through those 2 points. So now I'm just going to demonstrate with a few practice problems where we're going to identify each function as growth, decay, or neither. Then we'll use transformations to graph each function. From that point, I want you to just practice your vocabulary by identifying horizontal asymptotes, domain, and range, as well as end behavior. Okay, so in this first function, g of x, I'm going to think about what the parent function is. So that would be y equals, my coefficient would be -1, so -1 times 5/2 to the x power. So what did I tell you to choose always? 0a. So 0, -1. And then it's going to be 1 times a times b. So a times b here is going to be -5/2, which is -2.5. Now what are we going to do? Well, this plus 2 at the end means that I have a vertical translation up 2, so I'm going to add 2 to my y values. So my x values won't change, but my new y value would be 0, 1, and then 1, and let's see, -5/2 plus 2 would be -1/2. All right, I'm going to go and I'm going to do my horizontal asymptote. It's going to be shifted up 2 units. So now it's at y equals 2. I'm going to identify that because I am told in the direction to identify my horizontal asymptote, and I'm going to graph my points. So 0, 1, and 1, -1/2. So now you're like, well, why is this below the horizontal asymptote? So even though this looks like a growth function because 5/2 is greater than 1, we have this reflection, right? This -1 out front is causing our graph to reflect. So rather than going up like exponential growth does, it's going to do a vertical reflection and shoot downwards. Okay, so it's going to look like this until it hits those 2 points, and then it will dramatically drop. So the question is this growth? Is this decay? It doesn't really look like either, and that's the correct answer. This is neither. You know, I guess you could say, I don't know, it's not closest to either because it just doesn't match. All right, domain and range are shown on the screen, and the end behavior, practice writing it and check your answer. Here's my answer. On the left side, as x approaches -infinity, the graph is approaching +2. On the right, as it moves to the right, it is going towards -infinity. Okay, so when I take a look at 3, I start with my b value, which is 1/2, which is going to tell me this is going to look like a decay function unless I have a reflection. But my parent function then will be y equals 3 times 1/2 to the x power. I'm going to pick my points, 0 and 1, and then I'll translate. So 0 would be 0a, or 3. 1, when I plug 1 in, it would be the product of a and b, just these two. 3 times 1/2 would be 3/2. So now I will translate this. So what does it do? It looks like 1 left and 2 down. So I'm going to subtract 1 from my x's to give me -1 and 0. And I'll subtract 2 from my y's to get 1 and -1/2. I'm going to sketch in my horizontal asymptote, which is at y equals -2 now because of the shift down 2. And I do know that this is exponential decay, so it will look something like this. So I'm going to label this one so I don't forget as a decay function. So I answer that part of the question. Plot my 2 ordered pairs, 1 -1 and 0 -1/2. And this needs to look like a decay function. So it's going to be something, kind of missed my ordered pair. I'm writing with a fat stylus, so do better than I did. Don't miss your 2 points. Okay? And take a second, practice writing your domain, range, and end behavior. Hit play when you're ready to check your answer. Okay, think you're ready to move on to the final example. For this one, see if you can do it without my help. So press pause now and hit play when you're ready to check your answer. I will not walk you through this one step by step. If you're still struggling, please be sure to reach out with questions.